Okay, so here we go. So it's a Monday morning, yay, yay, but it's getting cooler, so I actually walked over here without getting all sweaty, which is nice. We're working in Chapter 6. Again, the administrative stuff is our first exam is going to be this Friday. So if you're in that, there's a section that has about 70 people in it. So if you're in that section, you need to be in the room that day. We'll pass the exam out, collect up what you have. If you do have any electronic, like MATLAB files or something that you would like to submit also, you'll be able on Canvas to go in and attach those. And I think I left the Canvas, I'll double check, but I left it open like 15 minutes after class so that if you have to go out in the hall and upload it, you don't have to waste your hour working on the exam, worrying about that. So, okay, so that's coming up. Let's see, there's some homeworks that are due, and here the exam only goes up for those, the first couple of, well, chapters 2 and 3, and here we are in chapter 6. So we're still driving on and keeping going. So where we're at, though, is we talked about for the reverse analysis of a robot, we're typically going to have a 6 degree of freedom robot, so if you add up all the freedoms of the joints, you'll get 6. And that's so the end effector will have 6 degrees of freedom. That means you can position, orient it at any desired pose within the reachable workspace. And the way we decided to attack that was in the reverse analysis problem, you're basically given where you want that last coordinate system to be in the fixed, so like 6 to F. And given that, then we made a couple of free choices to establish what we called an S7 vector, and then we closed the loop. And what we found is when we closed the loop, we got 3 distances, 3 angles came out of it. When we put it all together, we took our 6 degree of freedom open loop robot. Given where we want the end effector to be, we turned it with this hypothetical link. We turned it into a 1 degree of freedom closed loop mechanism. And our goal now for the whole bunch of the chapter is to solve these 1 degree of freedom closed loop mechanisms because they correspond to an open loop 6 degree of freedom robot reverse analysis problem. Okay, so to get there, we have to generate a bunch of equations then that relate, twist angles and joint angles, alphas and thetas, joint offsets and link lengths, S's and A's. And we're going to build up a whole big toolbox of equations. So to get there, for that whole big story, we want to analyze 1 degree of freedom closed loop mechanisms. What the video talked about on Friday was how to generate what's called an equivalent spherical mechanism. So here's an example of a mechanism. One link was fixed to ground. We did the mobility of this thing on the right-hand side. It's a spatial mechanism. It's 1 degree of freedom. So our typical problem statement on this would have been, given all the constant mechanism parameters, it looks like it would have been A12 through A51, alpha 1, because I know for all the links. I'm always going to know that. And then I looked at the joints and said, well, I know the distance S3 because it's a revolute joint. I knew S4. I knew S5, those joint offsets. It's a 1 degree of freedom device, so I'm going to give you one input, say theta 5. And then what we had to solve for here were all the unknowns. So it's theta 1, theta 2, theta 3, theta 4, and where the cylindric joints were, right, the distance S1 and S2. So that's our problem statement. Given all the constant mechanism parameters, given one input, find the remaining outputs. Now to solve that kind of problem, we need a bunch of equations that have, it's okay to have theta 5 in them. It's okay to have all the A's and the alphas. It's okay to have those joint offsets. I'd love to be able to, for example, find one equation in one of those unknowns, but right now we have no equations in our toolbox, right? We got nothing. Okay, so that's our goal, is to solve that problem that I'm going to erase right now. And to get there, we're going to start off by talking about these equivalent spherical mechanisms. So what we did is we took the S1 direction and brought it over parallel, and then I'm going to change color and say the S2 brought that over parallel. And we looked over here and said how the angle between S1 and S2 never change. Right, it's alpha 1, 2, there's a rigid body there. So I'm going to insert on this radius 1, on this unit sphere, I'm going to insert this piece of metal to keep that angle. Oh, and I should have brought over the A12 also, I just didn't draw it. But yeah, everybody's being brought over parallel. And A12 now is perpendicular to that plane that was formed by S1, S2 and the piece of metal. And then we did the same on the other links. We brought over S3 parallel and put a piece of metal in there to maintain the angle between 2 and 3 is alpha 2, 3, da, 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 da. And we did all that. And then we looked at this equivalent spherical mechanism, and just because, just like A51 link is fixed, this link over here with alpha 51 is fixed. And we look at the mobility over here. The magic number on the spherical mechanism is 3, right? Takes 3 pieces of information. I think that was on that slide. 3 pieces of information to lock it down, to know where it is. So the mobility equation became, oh, come on. I always forget. If I minimize this page first, it doesn't do that. The mobility over here was the magic number n minus 1 minus the sum of the freedoms of the joints, 3 minus f sub I, and all of these are 1 degree of freedom. So basically we got a 2 over here. Okay, so we generated this equivalent spherical mechanism, and then what we noticed though is that all the alphas and thetas over here are the exact same as the alphas and thetas over there. So any equations we can come up with over here for the alphas and thetas will be valid for this. And I think that sentence was underlined in the book. So pretty much, let's see, it's 8:36. So in the 6 minutes, we just did what was in that last hour video. Okay, so to get everybody back up to speed. Okay, so our goal now is to generate equations. Oh, the other thing is we decide how to classify these mechanisms. We're always going to have 1 degree of freedom spatial. We're going to classify them based on what's the mobility of the equivalent spherical. So this one would have been a group 2 because it's a 1 degree of freedom spatial whose equivalent spherical has 2 degrees of freedom. And when we classified all of them, these are all 1 degree of freedom spatial mechanisms whose equivalent spherical, the equivalent spherical mechanism has 1 degree of freedom, right? These have 2, these have 3 and 4. And these are going to be discussed and solved in Chapter 7, Chapter 8, Chapter 9, and Chapter 10 in the book. Those are going to be super easy. These are okay. These were people's PhD dissertations, so we're going to look at them from a scholarly point of view and said that was interesting that they did that. I don't know why they decided to do that, but it seemed to work. You're not going to be expected to solve those in an hour on a test. Okay, one other thing before we get into the main topic today is it's hard to draw that on the board. So I did that. I think I did that one in SolidWorks. A lot of times I'm going to represent it like this. So 5-1 is fixed. Joint 1 is a cylindric. Yep. Joint 2 was a cylindric. Joint 3 was a revolute. Joint 4 was a revolute. And joint 5 was a revolute. So I'm going to draw that on the board just because it's a lot easier than trying to draw that. For the equivalent spherical, I'm going to draw this. And the only difference is the cylindrics on the 3D mechanism got mapped over to revolutes on the spherical mechanism. So I'm going to do those bottom pictures a lot because it's so much easier to draw, but you're supposed to, in your head, you're supposed to see those things happening. Okay. So here's what we're going to be doing for today. Hopefully we'll get through a bunch of this one. We probably won't. We'll probably get to this one on Wednesday. But we're just going to do this exercise. It doesn't seem to have any logic or reason of why we're doing it, but it'll come together a little bit later. We're going to look at all our S vectors, like S1 through S7, and we're going to write down what would their direction vectors be in terms of the first coordinate system. Somehow that's going to help us to get, I'm going to go back to this one, equations that relate to alphas and thetas. So it's not going to get us there today, but that's just our weird goal. So don't worry about why are we doing this or what's going to happen, and it's just for the heck of it, okay? So is everybody okay? Not to be like, no anxiety is what I'm trying to say. So this is crazy. Why are we doing this? Okay? We'll just do it, and we'll see something good will happen in a couple days. Mm-hmm.
Just out of curiosity, is there like a group 5?
Oh, so is there group 5, group 6? That's a real good question. I should have mentioned that on the video even on Friday, and I didn't. The reason we stopped here is, for example, well, how come I don't have 8 revolutes? Well, that won't be a 1 degree of freedom. So you can't have a 1 degree of freedom and get any more complicated. So that was, I hope I repeated the question. I'm supposed to, there's a big sign here that says, please work for the people at home. But so the question was, how come we don't have, group 5s and stuff? And that's because we're going to stop at where 1 degree of freedom, and you just can't get there. And I was supposed to say that on Fridays, and I remembered that I didn't. So, man, you guys are good. I can't get away with anything here. Okay. So we're going to go for these S vectors in the first coordinate system, and the first one's going to be really easy. You know, S1 in the first, right? Because the first coordinate system has, you know, for the spherical mechanism, right, all the origins of those coordinate systems are at the middle of the sphere. And the Z is along S1, and the X is along A12. Right? That's our standard coordinate system. So that one's really easy. So now we have to go for S2. We're going to go all the way up through S7. So one thing we're going to need to get there, and I'm going to have to write it on the board, but I need to see it, is this matrix R2 to 1. So I'm going to write it over here. I'm trying to think how much board space that I want to use. So R2 to 1. Remember, coordinate system 2 was aligned with 1. We translated it A12 along the X, rotated alpha 12 about the X, translated capital S2 about the Z, and then rotated theta 2 about the Z. And when you got the upper left 3 by 3 of that, it was cosine theta 2, sine 2, cosine 12, sine 2, sine 12, minus S2, C2, C12, C2, S12, 0 minus S12, C12. Okay. So that was, you know, because we attached our coordinate systems in the standard way all the time. So the second coordinate system, the Z is along S2 and the X is along A23. Okay, so if I want to, you know, obtain S2 in the first, well, I know S2 in the second is, what, 0, 0, 1. And I know that to transform a direction vector, we talked about that in the earlier chapter, if I pre-multiply it. Okay. So I'm going to rewrite it down here. Minus S12, C12. Okay, S2 in the second is 0, 0, 1. So when we go for S2 in the first, right, it's row by column, so we get a 0. And then row by column, basically we get that last column. All right, so that's S2 in the first, so no big deal. 0 minus S12, C12. And again, this isn't very hard, but it's not real exciting either, but we're just going to go for it. Just keep going all the way through S7. Okay. So the next one we want, S3. So we come up here and say, all right, and I know S3 in the third is 0, 0, 1. Oh, I got to post-multiply this by, right, to get R3 to 1. I have to take R2 to 1 and post-multiply it, and it's starting to get messy. We're going to do a little bit of a shortcut here. Okay, I know that's true, because if I did, and of course right now I don't have S3 in the second, right? I get S3 in the third. But if I did have it, R2 to 1 would give me, S3, that's what I'm looking for. I need to get the eraser. Okay, so how can I get S3 in the second? Oh, well, I could do this. Right, do this right, and I know that's, I finally got something I know, 0, 0, 1. Oh, and I could get this by adding 1 to every indice here, and then I'm going to speed this part up. I'm going to say, you know, I've got S2 in the first. What if I add 1 to every one of these indices? Will I get that? And we will. So I'm going to do a shortcut and say that S3 in the second is going to be, I'm going to just write it over here, 0 minus S23 C23. That's going to save us a bunch of time to take this and just add 1 to the indice. You're going to get the exact same thing as that. Because here, I would have added 1 to the indice and taken the last column. Yeah, I would have gotten that result. So that's going to speed things up a little bit for us. Okay, and then we're just going to brute force, multiply this out. We're not doing any magic. So we do row by column. So row by column, the top element, I got a negative and a negative, is going to be S23, S3. Okay, and this is what we're getting, S3 in the first. Okay, row by column, I'm going to group it, let's see. So I got 0 times that. I got a negative, and there's another negative. I'm going to pull the negative out front here and then put it all in parentheses. I'm going to write this times that first. S12, C23. Didn't have to. Plus that times that. C12, S23, C2. You say, this is kind of boring, right? But we're not cheating or anything. We're just knocking them out. And then for the last element, I got to do row by column. So I got 0 times that. And I'm going to write that one first. C12, C23. And then I got a minus sign. S12, S23, C2. Oh, yep, no, we're okay. C2, yep. And then we go to write it down. And you say, holy cow. Then we start to get a little bit nervous, right? Because what happens when we get to S7? Right, it's going to get pretty gigantic. Because when we do S4, I'm going to take S4 in the second by adding 1 to all these indices and jamming it over here, and it's going to get really ugly fast. So this is something Dr. Duffy came up with. He said, I'm going to introduce some notation. He says, whenever I see this combination of terms, I'm going to call that X2 bar. X2 with a bar over the top. And whenever I see this combination of terms, I'm going to call that Y2 with, and don't worry about why is there a bar over the top. Oh, you know what I love about definitions too? Nobody can say you're wrong, right? You just define this. Nobody can say you're wrong. If that's what you want to do, you just have to remember that every time I see this chalk, it means that. Sine alpha 2, 3, sine theta 3. And every time I see that chalk, it means that. But boy, look what happens when I write this down. Boy, it saved a lot of chalk. So why did he come up with this notation? Oh, I got a mistake here. Okay. Why did he come up with that notation? Okay, the one thing he did is if you think about what we're doing here, right? They have alphas and thetas in them is all. We're getting the directions of all the S vectors in terms of the first coordinate system for some strange reason. And all these expressions have only alphas and thetas, right? Because we're only doing the orientation, the direction parts. Okay, when we do our robot problems, we're going to know all the alphas. I'm never going to give you a problem or a test problem especially and say, well, I'm going to switch it around this time and tell you, here's the thetas I want. You design the robot by figuring out the alphas. I'm not going to do that. We're always going to know the alphas. So the reason he went with the 2 over here is to indicate that this definition has theta 2 in it as the only theta. You want to know in that expression, what are the thetas that are in there, because the thetas are the unknowns. So that's why we have the subscript. And then he said, later I'm going to see some patterns, like I might see S3, 4, S3. And I might see S3, 4, S4. And I might see all this, or let me change that. I might see that, but I might see 2, 3, S3. And I might see another S negative SC plus CSC and a CC mod. So we're going to go ahead and look at this single subscript notation. In case we do see those other things occur, those patterns, we will be able to do this single subscript. I call it substitution. And I've got a picture in the book that is how I remember these. So imagine, well, let's use what we got there, X2 bar, Y2 bar. So when I see those symbols, I think of this picture. There's S2, and then what's the link that came in here? Alpha 1, 2, right? Alpha, so I'm drawing part of the spherical mechanism. So I think of that picture in my head when I see this, X, Y, Z notation with single subscript. because it has to do with theta 2. And theta 2 is the angle between, right, A12 is perpendicular to the plane. Right? I didn't draw the S1, but if I did, right? And this plane here, I didn't draw S3, but you know, it would be perpendicular to the plane formed by S2 and S3 and that piece of metal on the spherical mechanism. And we know that theta 2 is the angle, well, you know, between those perpendiculars. So it's also the angle between the planes. So you think of those planes. So I could even visualize theta 2 as being right there. Okay, so when I see this single subscript notation, this picture jumps in my head, and I sketched it in the book, but I think I used I and J instead of 2 and 3, or theta 2. Okay, so how do I remember what this notation is? I'm going to use 3 equal sign, or an equal thing with 3 to indicate it's a definition, and I did not do that in the book. I should have. And I have to remember, first of all, when I see this stuff, what's the pattern? SC negative, SC plus CSC, CC minus SSC. That's going to be our pattern. That's what we had over there. That's what appeared. Also, when I took this class, it was closed book, which it's not for y'all, okay? So I had to memorize this, and then I took it since 1979, so that's 21, 40, holy cow. So I've had like 46 more times to go through this. So I still got them up here. It's kind of my test that I'm not going nuts yet, as I can remember this notation. And then I say, okay, I had to remember the pattern. And the way I remembered the pattern is I came down, I saw there's one minus sign here and one minus sign there, and this kind of stood out. CC, it sounded like a name of a poodle or something, you know? I go, CC. So if I got a CC there, minus SSC, and then I had to mix it up, and oh, even had a mistake, right? It's SS, so I am losing it a little bit as I get older. So I get a cup of coffee. So the first thing I would do is I would remember the pattern, and then I just stared. I had to memorize it because it was closed book. I stared at this and said, you know, that theta 2 only appears at the very end there. Everybody else is an alpha, and the alphas that are in here are the ones that touch S2 in my picture that's in my head. So I said, okay, I got the pattern, and I come up and go 2, 2, 2. And then these are all alphas, everybody that's left. And they're going to be the alphas that are touching S2, so they're either alpha 1, 2 or alpha 2, 3. And here's how I remembered it. When I saw this bar, again, this is just stupid stuff of how I memorized this, I said, I'm going downhill. I'm coming downhill. I got to alpha 2, 3 before I got to S2. So, and again, this sounds stupid, but I've done it for how many years. Alpha 2, 3 wants to be closer to its friend theta 2. And everybody else is 1, 2. So, hopefully that matches. I mean, that's just what happened when we took, you know, R2 to 1 times S3 in the second. That's what came out. And Dr. Duffy decided to save some chalk and said, I'm just going to call them X2 bar, Y2 bar, and Z2 bar. So let's use the same picture, though, and let's do without the bar. Because that might appear. It didn't appear yet, but it might someday. And it turns out that what he did for this notation is the same pattern. SS negative SC plus CSC, CC. And then all those little memory tricks I had over there still work. I just want to move that 1, 2 up here. So if that definition was written, it represents, again, put a 2 at the end. There's no bar on top, so I'm going uphill. So before I get to the S2 vector, I got to the alpha 1, 2. Alpha 1, 2 wants to be near its friend theta 2. And then you get to 2, 3 afterwards. So if, you know, this, I see a lot written on the board somewhere, and there's no reason for it to be on the board because we haven't seen it yet, but if it ever did appear, that's what that definition would be. And I had a way to remember it, and you know, I was doing okay. Okay, a couple of things about these definitions. What if I was to take this and square it, and this and square it, and this and square it, and add them together? Now, we could go, and Maple is real good for that, right? Because I could go symbolically, and then I could tell it that S23 squared plus C23 squared equals 1, and it would this squared plus this squared, by definition, is going to reduce to 1. And I should do it in Maple. I probably have a Maple spreadsheet all ready to go. But I'm going to get around it this way. This is a unit vector, right? S3 in the first. So its x coordinate, its x direction values, that squared plus that squared plus that squared have to add up to 1 to be a unit vector. So it will symbolically. So if I was to go into Maple and write this all out and then apply those trig identities about how the sine squared of theta 2 plus the cosine squared of theta 2, that reduction, that grouping would happen, and it would equal 1. The other thing to notice is, look at the definition of Z2 with a bar and Z2 without a bar. There's a symmetry there. They're the same definition. That's okay. So those are the two odd things about these definitions. But boy, it saved us a lot of chalk. I'm trying to peek at the clock. Okay. So again, it seems weird. Why are we doing this? And I'm not even worried about that much. Why are we getting all these S vectors? But we're just doing it. And one reason we're doing it is we're introducing this notation because that's going to appear in the future. Okay. So we're ready to go to the next one. Got S1 in the first was easy. S2 in the first was the third column of R2 to 1. S3 in the first, saved a lot of chalk with that definition. So now we're going to go for S4. At least I caught myself that time. I know this is true. If I had S4 in the second and then 2 to 1 it, I'll get it in the first. So to get S4 in the second, I could take S4 in the fourth, and I've got to do this, 4 to 3, 3 to 2. Multiply that out. This is 0, 0, 1, blah, blah, blah. Or I'm going to go here and add 1 to every index. And I'm going to get the same result. I'm going to say S4 in the second is going to be X3 bar, Y3 bar, Z3 bar. Oh, what's X3 bar? Oh, how about, yeah. What's Y3 bar? Oh, 3, definition. What's Z3 bar? Negative SC, CSC, CC. Oh yeah, and the 3 goes at the end. And I'm going downhill, so I get the alpha 3, 4 before I get to the S3 vector. So 3, 4 wants to be near the neighbors. And then who's left after I get past the S3? I get to alpha 2, 3. So it saved us a lot of chalk writing, to just call it X3 bar, because I know what they are. Don't feel like writing all that down, though. So now, to get S4 in the first, we're going to go ahead and do the, take S4 in the second and bring it back through R2 to 1. Row by column. Oh, my goodness. X3 bar C2 minus Y3 bar S2. Right, that's the... and there's no magic here. It just seems it's kind of boring, but okay. Row by column. I'm going to group it by, see that C1, 2? Okay. I'm going to pull that out front. And then I'm going to have X3 bar S2. Then I'm going to have a plus Y3 bar C2. I just grouped that out. And then I've got this next one, minus S12 Z3 bar. Got no magic, just row by column. And then we're going to do row by column to get the last one. I'm going to pull that S12 out front. And when I do look at what's left, in the parentheses here is going to be the same as what we had in parentheses. And then the last term is a plus. And then you say where, of course, x3 bar, y3 bar, z are defined over there on the other board. On the other board, there's no magic or anything. It's just super long and complicated. But so now I can come over here and say S4 in the first, and I would write all that down. Dr. Duffy introduced another new notation. That's an awful lot of chalk up top. I'm going to define this. Let me use colored chalk here. I'm going to define that as x32 by definition. Oh my goodness. I'm going to define this combination to be y32. And I'm going to define this combination of terms to be z32. Okay, so what's nice about the subscripts, the 2 and the 3, is that this definition has only those 2 thetas in it, right? There's no theta 1 or theta 5 or theta 7 or any, it's just so that's what's nice about the notation. There's a bunch of alphas in there, but we know the alphas in our problems. So he's indicating what thetas are in those definitions. So when I come over here, though, I can just save a lot of chalk, x32, y32, z32. And then I'd say, oh, well, where, by definition, x32 is this. And then I would say, where, by definition, x3 bar, y3 bar, z3 bar, are on the other board there. And if you did put them all together and try to write them down, the odds are pretty slim you wouldn't do it without a mistake. But Maple would do it. They don't care, no problem. But they were starting to get a little bit unwieldy, if you were to just substitute the y3 bars in here, and then especially try to write it all down. But with this notation, I know what I mean by that because I know those definitions. But it's like, oh my goodness, these definitions, it's like, boy, I hope they stop, right? We don't want a ton more. And for today, it's not going to get much any worse. But, oh, here's one thing. If you ever think I'm asking a problem where I say, like, define x32, and I expect you to take that board and jam it in here and come up, I'm never going to ask you that. So if you think that's what I'm asking, you're thinking, I'm not asking the question correctly enough. Because we don't want to have to do that. I don't care if Maple does it, but I don't want to ever do that. We want to take advantage of our notation. Okay, so what about this double subscript notation? We see what x32, and in the future, we might see, for example, x23. It's like, oh my goodness. So let's look at those combinations. Well, we're never going to see like x24 or something. The numbers are going to have to be adjacent. We're never going to see something crazy like that. But I've got on the board over there x32y. So what if I did have 23? What if that did pop up? And I'm going to say, what would those definitions be? And then again, I had to memorize them. So here's the pattern. I stared at what was in there, and it looks like xc minus a ys, a cosine xs plus yc minus a sine z, and then a sine So I looked at this one, and again, because at 1979, I'm sitting in the back row, and it's a winter time, and the class is at night, and whatever, and I'm just staring at these. I got to come up with a way to remember these. And the way that I remembered the problem was this thing in parentheses. And I remembered this word, excess. And I said, hey, excess is in the parentheses, okay? So that was my way to remember him. Then, was it the 80s? There was a band. Anybody going to remember? That was even better. In excess, the excess is in the parentheses. So I think the guy was Michael Hutchinson or something was the lead guy. In excess, or Hutchins or something like that. So that's how I remembered it. And then I said, well, if XS is in the parentheses, well, I got to have something different up here, so it's XC. And oh, wow, there's a couple of minus signs. This one doesn't have a minus sign. And wow, the sines and the cosines. And the way I remembered that is, in my head, cosine is better than sine, okay? And the reason is the cosine curve is symmetric about the origin, and the sine is not. So I think the cosine is better. So the cosine gets the positive sign. So the negative must be there. Well, if this, so the cosine's got, so I came up with all these stupid things. So I got CC the poodle for the single subscript, and I got in excess is what makes me remember the pattern. Okay, once we got the pattern, I stared and stared and stared over here, and I said, wow, X23, 2, 3, 2, 3, 2, 3, 2, 3, 2, 3, 2, 3. Oop, I can stop there. Oh, 2. And then I looked at what's left, and let's see, 3, 2, and then there's one alpha that's left, and they're all the same. And I came up here and I said 3, 2, the next number is 1. I don't have an alpha 2, 1, but I got an alpha 1, 2. I come over here and I say 2, 3, the next number is 4. So if we ever see, X23 written down, its definition is that, although we haven't seen it or anything, but if we ever did, that's what it would be. The other difference was here, when I looked at this definition that has 2 subscripts, 3, 2, I'm going downhill. I needed the downhill indicator, the bar. I overwrote the bar on that one, but 3, 2, oh, so when I go to this pattern, I go from double subscripts to singles. I'm going down, and then over here, I was going uphill with 2, 3, so I did not put the bar. Because remember, X2 is different than X2 bar. So it's important to catch all those little subtleties. So a lot of times you get to this part of the class, and it's like, we're going to be okay. It seems like, how am I ever going to deal, especially the first time you see it, how am I ever going to deal with this notation? Well, if I see X32 written down, there it is, and it's open book. So you can dig in and whatever. But again, when I took it, holy cow. Okay. So at the moment, easy, not too bad. We introduced this notation, so we didn't have to use as much chalk. We introduced this notation because it was starting to get big. So we're ready to go for S5. Okay, so we're going to get rid of this. And happily, this is going to go pretty well. Oop. Don't need that. Okay. S5 in the second. I'm going to add 1 to all these indices. I'm going to get or I could do it the long way, but so S5 in the second is going to be X43, Y43, Z43. Where, let's write them down. What's the definition of that? You're saving chalk, but it has to be, it's going to be an XC minus YS. It's going to be a cosine. It's in excess. And then, there has to be a minus sign. Okay, so 4, 3, I go 4, 3, 4, 3, 4, 3, 4, 3, 4, 4, 3, 4, 3, 4. And then there's 1 alpha that's left, and I say 4, 3, the next number is 2. So I should have written all that chalk over here. And then I do have to say, where? Holy cow. And I messed up, right? I messed up. It's downhill. It was downhill. I had to put the bars on top. I messed up. Where X4's definition, SS, y4 bar's definition is negative SC plus CSC, and Z4 bar CC. And I go 4 and 4 and 4, and I'm downhill, so I get to 4, 5 before I get to 4. 4, 5 wants to be near its friend. And then after I get by S4, I get to 3, 4. So, you know, when I wrote S5 in the second, I didn't use much chalk, but holy cow, all that stuff is in there. I just didn't have to use that much chalk. So if I did ever say fully define these terms, this is what I would expect you to do on the paper. You'd say, oh, well, here they are. Oh, where? X4 by Y, you know, where? And then it is fully defined. And again, if you substitute everything in there, this thing's going to be a big mess, but it is what it is. Okay, so guess what happened when we go ahead and row by column now? XC minus YS. The next row by column, I'm going to pull the C12 out front, and I'm going to have I'm going to have XS plus YC, and then a minus S12 Z43. And the last row by column, I'm going to pull the S12 out front. And I'm just writing it down because I know what it is without having to look, so I'm cheating on you. That's supposed to be 4-3. We're not doing anything magic. We just took S4 or S5 in the second and just brought it back to the first, and this is what came out. Dr. Duffy says, you know, I'm going to define that to be X432. I'm going to define that whole mess to be Y432. And I'm going to define that whole mess to be Z432. And you say, oh my goodness, is this ever going to end, right? This notation. It's not bad now, though. We had the single subscript notation where the format was SS, negative SC plus CSC, and then CC minus SSC. And then we've got the double subscript notation. Notice the pattern is the same. There's an in excess, XS plus YC, the minus sign, the plus cosine. The pattern is the same. So hallelujah, we don't have any more memorizing of patterns. It's just how do we fill in the letters. So here's these definitions so nobody can say you're wrong. So we're going to go ahead and write it as X432, Y432, and Z432. In a minute, we're going to get S6 in the second by adding 1. So let's write down that definition. Let's add 1, because in other words, I don't need to rewrite X432's definition on the board because there it is. But let's go over here. Just trying to think of, I just want to leave this pattern. I'm going to run out of board space. Getting rid of all of the stuff at the moment. Getting rid of all of that junk because we're going to, only thing is I'm going to need more board space, and I already used up a lot. Okay, so we've got S5 in the first, and again, it's nice, the subscripts tell us what thetas are in there. If you were to jam everything into some giant expressions, this expression has theta 2, theta 3, and theta 4 in it. And a bunch of alphas. Yeah, I don't care, I know all the alphas. And if I did want to totally expand it, I would have said where X43, I just erased it, and then where, you know, X4 bar, Y4 bar, Z4 bar. Okay, so we got 5 minutes, so we're going to do we're gonna do it. Oh. I need to get S6. I need to get S6. Okay, I'm going to get S6 in the second by adding 1 to every indice. I mean, I could multiply it all out and it would take us another period to do, but so I'm going to say S6 in the second is going to be X543, Y543, Z543. Oh, where by definition now X543 is an XC minus YS. Y543 is a cosine XS plus YC minus a sine Z, and Z543 is a sine. So yeah, I know what it is. I saved a ton of chalk writing it that way, and then I'm going to go 5, 4, 3, 5, 4, 3, 5, 4, 3, 5, 4, 3, 5, 4, 3. And then there's one alpha left, and the next number is 2. This is just the way that I memorized it. There's no scientific anything at all about it. And then I would say, oh, where? X54 and Y54. Oh, and downhill, so I need the bars. 5, 4, 5, 4. 5, 4, 5, 4, 5. 5, 4. The bar. 5, 4, 5. 5, 4. The next number was 3. Oh, and then X5 bar and Y5 bar and Z5 bar. I put the 5. I'm going downhill, so I get the 5, 6 before I get to S5. So 5, 6 wants to be near its friend theta 5. And then after I pass the S5, I got the alpha 4, 5. So I'm having flashbacks to a night class in 1979, and when I walk out of here, I expect to see snow on the ground. So it's like, holy cow, that was a lot of stuff, but hey, I know what all those terms are. Saved a lot of chalk. So guess what happens now? We got 4 minutes. We're going to do row by column. Row by column. I'm going to get X 543 C2 minus Y 543 S2. I'm going to get cosine 1, 2. XS plus YC. I'm running out of room here. Minus SZ. The last row by column, S12 X S plus Y. So the pattern's the same. Hallelujah. And then Dr. Duffy looked at this top thing and said, I'm going to define that to be X5432. And I'm going to define that to be Y5432. And I'm going to define that to be Z5432. So now I can, without using much chalk, 5432, Y5432, Z5432. And again, when I see the multi-subscript notation, I know that those terms would contain those thetas and a bunch of alphas, but I know all the alphas again. And what else? Multi-subscript. So I know what the pattern is. XC minus YS. Oh, in excess. Yeah. Oh, now the 5432, I got 543s. Yeah, I got that on the other board here. And that expanded to give me 5. Oh, yeah. Oh, I needed to put bars because I can indicate downhill by the numbers on multi-subscripts, but on single subscripts, I need the bar to indicate downhill. And so holy cow, it's a complicated expression, but we saved a lot of chalk. And we're at the end of class. There's 1 left to go. Is S7 in the first? We're going to add 1 to all of these subscripts and do all of this stuff. And here's what you're going to get. It's going to be X 65432. Now, without the notation, it would have taken this board plus that whole board on the side of the thing to probably write it all out, right? Because of how complicated and messy and the odds of doing it by hand. I always wondered if like Isaac Newton and people had tools like Maple, they would have gotten 5 times more done. So that's what we did today is, he said, don't worry about why or whatever, some kind of strange thing, but if I want to get all the S vectors expressed in the first coordinate system, there they are. I just have to remember what this notation, what those definitions are. Because without the definitions, they just got super long and complicated and messy. So again, don't have anxiety, right, about this. Why, just say, yeah, okay, I don't know why we did that today, but yeah. Basically what we did today is we introduced this notation. It's going to help us a lot. Right, none of this is on the first test, so everybody's like, I'll worry about it in a couple of weeks, but no, hang in there. Okay, so we'll see you on Wednesday.